So I'll present you, as René said, two workflows that are very important when it comes to interpreting seismic datasets. These are Seismic Spectral Blueing and Seismic Coloured Inversion. In a nutshell, what are these two processes doing? Seismic Spectral Blueing has for objective to map the seismic spectrum to the well spectrum in order to recover missing frequencies within the seismic bandwidth. It provides input for relative impedance inversions, and it also provides input for small-scale fault interpretation. You can see on this slide comparisons between an original dataset on the left-hand side, an inline section, and a blued seismic dataset after seismic spectral blueing. On the other hand, the seismic colored inversion has a completely different objective, since it aims at inverting the seismic data using a fast band-limited inversion approach. It doesn't require any wavelet estimation, and therefore is a very fast workflow in order to go from seismic data, which is you see on the top-hand side of this slide, to inverted data, where you can much easily see a flat spot occurring on this data set. These techniques are described in a paper by David Whitcomb and Steve Lancaster that you can get from the SCG website. Let's give a small word on impedance inversion theory. The Earth's reflectivity amplitude spectrum is blue. Therefore, this means that the amplitude of reflections increases with the frequency. This information can be retrieved by applying a Fourier transform on time-converted reflectivity log. This is part of what is being done in the workflow. The inversion itself is the process that will estimate the Earth's impedances from the seismic reflectivity. Therefore, any inversion workflow must remove the wavelet, in other words, estimate impedance from seismic amplitudes. There are two approaches in order to achieve this goal. First of all, we can reshape the seismic data using the amplitude spectrum and phase spectrum from the seismic. A number of inversions that can do it. Some are trace integration techniques, recursive inversions, and colored inversion is one of these three methods. The input requirements for the first two are that the seismic input is zero phase and blue. Once again, it means that the seismic reflectivity follows the Earth's reflectivity. And these are processes like seismic spectral blueing, wavelet deconvolution, or spiking deconvolution. All three terms are synonym from each other, roughly. The seismic reflectivity is then directly mapped to the impedance reflectivity, and we add a -90° phase rotation in order to convert reflectivities into impedances, relative impedances. A parametric inversion can be used in order we'll use the convolution model to formally remove a previously estimated wavelet from seismic traces. The addition of an additional low frequency model enables the creation of a broadband absolute impedance output. These are specific methods or model-based algorithms. The workflows for both seismic spectral blueing and seismic colored inversion are very similar. They all comprises 4 steps. The first step is the extraction of the seismic data using a small user-defined number of traces of input locations, from which we compute the mean spectrum that is smoothed in order to get the smooth seismic spectrum. That is the end of the first phase. In the second phase, we are trying to extract the same data from the wells, which means that in the first place, we will extract the well reflectivity spectra for spectral blueing, or we'll extract the well impedance spectra for colored inversion. Then from both, we compute the mean and fit a curve through the mean. The third step of both workflows is the real step where the operator is being built. The operator is built by subtracting both mean amplitude spectra by keeping either the phase distribution untouched for spectral bluing, or by applying a -90 degrees phase rotation for colored inversion. And we apply an additional bandpass filter and convert the spectrum back to time in order to get an operator. The operator will most often is a similar quantity as a wavelet. So we get the output by convolving the seismic data with the operator. Not deconvolving, but we convolve the operator with the seismic volume. I'll now go through a demo of both workflows. It is used for this workflow the Stratton dataset, which is a real dataset from Gulf of Mexico, for which I'm showing here a section through the seismic data. I can also similarly load a number of wells that have been loaded in OpendTect at various locations. So here I have 3 wells, and so these wells contain the deviation survey of the well, some input markers, but also the key logs we need to use. So these are the 3 impedance logs we might use for both workflows. Now I'll start by opening the attribute set window. The attribute set window is where both workflows, colored inversion and spectral bluing, are located. The attribute engine of OpendTect will take care of the computation of the output volumes. But prior to the computation, we'll need for both workflows to analyze and create the bluing operator. The pressing of the Analyze and Create button will launch a standalone window that can be that is used on top of OpendTect. If there are any questions with respect to either the software or the workflows, you'll find in this disclaimer box all the details on where to contact us. The first step, as I said previously, is to retrieve the data. Then first press on the very first icon here in the toolbar, where I can retrieve my seismic data and load a subset of the volume. These can be 40 traces, more or less, it depends. And as a second step, you can see that the data has been sent to the chart while I was selecting it. I'll also load in a very similar way the wells. First of all, in this window, this will load the wells loaded in OpendTect with a list of logs that are suitable for this process. That is either an impedance log or any set of sonic and density logs. So I could create on the fly impedance logs by selecting sonic and density. So as I'm selecting the wells here, you can see that the charts are displayed at the same moment, and that I'll be able to go on by selecting the data. Need to shift. I'm working with 2 screens, so I need to go back to the same screen. Once again, I select data, load a few traces, and I load the wells and the corresponding impedance logs. Then I can close this window, and I'm already done with the 2 steps of the workflow, with the 2 first steps. Nevertheless, in order to go a bit further, I'll first present you all the details that you can see in this chart. If I zoom in on this chart, you can see the seismic mean spectrum here, using Control-Shift to zoom in and out. So for this data set, the black curve represents the smoothed mean seismic spectrum. So we can see that we have a dominant frequency at about 35 Hz with data. So if I go 10 dB lower, somewhere between 13 and 63 Hz. Now this mean spectrum in black is not very smooth, at least not enough for me. So I'll open the next processing window, which was this icon, where I can really design my my operator and its important parameters. So if I increase this low cut parameter, you can see that I can smooth further my curve. And of course, I need not to go too far because the input shape must remain preserved. So somewhere for this data set, the compromise lies between probably 15 and 20 Hz. I need to do the same work with the well data. So first of all, since I'm doing seismic spectral blueing, I have extracted, the software extracted for me impedance logs in the time domain. So they are already time converted, resampled, upscaled at 1 milliseconds. That's what we see in this chart. And the second chart presents the corresponding well reflectivity logs in the time domain once again, whereas the third chart from the well data presents the well reflectivity spectrum. So if I summarize, these are the impedance logs, reflectivity logs in the time, and reflectivity spectra, one for each well. Once again, the red curve in the fourth chart is the mean of all wells, and the black curve represents the smoothed mean. Sorry, this is a curve fit. That was a smooth fit, while this is real curve fit. And the curve fit is done between two specific frequencies that are the low and high cut frequencies. So for instance, I can see that the match is not very good yet. If I change the scale to a linear scale for both charts displaying a spectrum, I can see that my data is becoming rather flat after a specific frequency, whereas the curve shows that it should be increasing with frequencies. Now, if I lower the high cut value, for instance, to 200 Hz, I can force the curve fit to become flat after this high cut frequency, which is here. For the low cut, I can also alter its value, and you can see that it will affect mainly the other end of the spectrum. If I go back to a log scale, it's much easier to see the effect of the low cut parameter, and most often I'll choose between a fit with a low cut at either 0 or 1 Hz when it comes to seismic spectral blueing. Now what we see as well on a linear scale is that the curve fit a bit, which is here above 200 Hz, slightly overestimates the data. I can go to the advanced controls, and in the section saying above principal, that is automatically set to force horizontal, I could set this to any value. Like if I set this to 4, you can see that the plateau has went a bit down. It's a bit too much. 4.2 seems to be more reasonable. Once again, so I can adjust very accurately the fit parameters, because from all this is the most important curve, this black curve, because we'll try to reshape the seismic spectrum, which is represented by this black curve, back to this black curve. That's why it is rather important to have it fit the data as much as possible. Now this black curve here will be repeated in the next chart, where we'll design the operator. It will be repeated as the green curve we see here, except that there is an additional bandpass filter that has been applied between this black curve and the green curve over here. The red curve is the repetition of the smoothed low-pass seismic spectrum, and the operator as such is the blue version. So red is the seismic, green is the bandpass well spectrum, and blue is the operator in the frequency domain. Yes, I can adjust also the low cut and high cut parameters that are the main difference between this black curve and this green curve over here. So, for instance, if I believe the high cut is set to low, I can change it, and we directly see the effect on the operator, both in the frequency domain and in the time domain of both ends. But most often, I will not decide on these parameters based on these two charts, but based on a blind test QC that is displayed underneath. This blind test QC is performed in such a way that will apply the very same extraction settings to 40 other traces in the volume or in its subselection. But instead of taking the seismic data as it is, we'll convolve on the fly these new traces with this operator displayed here. And therefore, we'll be able to QC if the spectrum after seismic spectral bluing matches the well spectrum in green, which is the same between these two charts. And the difference is displayed in blue. So we see here in blue, especially where the amplitudes are going above the zero line, the areas where we are actually overfitting the data. And we can circumvent this most often by adjusting the low cut parameters and high cut parameters. Most often by increasing the low cut value or decreasing the high cut value. And as a rule of thumb, we can use for these two low cut and high cut values the frequencies at which we would have at which we really don't have data anymore. So if we have a peak of frequencies at 100 Hertz, we could cut either 10 or 15 dB, or most often I use as a rule of thumb 10 dB, so between 13 and 63 Hertz. And you can see here that I'm really not far with these two figures of having a very good QC operator, which is flat. Now I can go on with the workflow. This is more or less the end of the third step, so the real design of the operator as such. The only issue, if you look at the amplitude of the operator, is that the amplitude of the operators may be very small. They are very small if your seismic amplitudes are very large, because we are subtracting both spectrum. So the blue spectrum here has much larger amplitudes than the normal seismic data. And there is an operation we can do. We can go in the advanced control and set the operator energy to 1 in such a way that that will have about the same amplitudes between input and output. Now there are only three more things I need to do. First of all, I'll save this session. So that will be my bluing session. I had already one, so I'll make one. I'll save it. And I can save the operator. Let's make one more bluing operator saved in the database, in the OpendTect database. Now I can minimize this chart. Well, I'll simply close it for now. And you can see that the bluing operator has been pre-filled in the OpendTect attributes. The only thing that is remaining is to provide a name for this attribute. And the work done by this attribute will simply be to convolve the input volume with my bluing operator. I've specified a name in the attribute set window, pressed add as new to load the attribute definition in memory. Now I can go a bit further and press OK. Now show the very same data as before. This is the input seismic data on one inline. And I'll add a new layer at the same location in order to first of all, apply my attribute on the fly only on this section. And since I have both at the same location, I'll be able to very quickly toggle on and off between the input data and the output data. What you can see here, you can see much differences there are in terms of vertical resolution on these data sets, especially in this area, which is below one of the input horizons. We have quite a very thick package, a very thick event here on the raw seismic that is far better resolved after spectral bluing. You can see if I toggle on and off quickly. So some events did not move at all, or nearly didn't move, while some events are completely different. And that is something I can keep in mind in terms of QC, is that the output should not be monotonous and single frequency. I should still be able to distinguish different apparent thicknesses into my seismic layers, except that there are more frequencies present after bluing. I can also QC a bit further by using some OpendTect tools that can display the amplitude spectrum of the data for a particular section. That is the amplitude spectrum of the input seismic for this inline, for all the points you see on this inline, and I can get the same for the spectral bluing attribute, once again for this inline. So you can see that we have moved from this kind of amplitude distributions, quite a very round shape around the dominant frequency, to a data set that is more constantly increasing in amplitude with frequencies until we don't have data anymore, until we are on the edge of the bandpass of the data. Now I'll go a bit further. I'll go a bit quicker through the other workflow because it's very similar. It is the colored inversion workflow. Once again, you don't need to do much in the attribute set window. Change the attribute type back to colored inversion. Seismic input is the same. And I'll press Analyze and Create to get, this time, a seismic colored inversion window. You can see that the row chart is very similar to the one we had before. Input settings will be the same. Once again, we'll load 40 traces. I could load more. It's a user-defined setting. I'll select the impedance logs I wish to use. Let's be slow. Once again, I'll load my wells. And close this window. Then the first chart is exactly the same. We have extracted the seismic data in the very same way. Then the third chart here is once again about the same. We still see the impedance logs in the time domain, but because we are about to extract impedance spectra this time, we'll have to do one more operation. Instead of creating reflectivity logs, we'll create detrended impedance log. The detrending option is something we have to do before we go into the Fourier domain, before we compute spectra, that is only a stabilization of the Fourier transform. So what you see here as black lines, these are the trend lines that are extracted from the impedance logs versus time. So we get detrended impedance logs and their spectra, one for each well, color-coded. Then the red curve is once again the mean, and we can see that it drops back to 0 because we have removed the trend. It doesn't mean that there was no data in the original logs. And the black curve is once again the curve fit through the data. And if I go to a linear scale, we can see that this time the data distribution does not become flat at a specific frequency. More or less the behavior is different. It's not like what we have seen with reflectivity logs. And then I'll be able to adjust my curve fit once again with the very same settings. We had used before a seismic smoothing of 15 Hz. That remains about the same. 15 Hz it's reasonable for this application, and we'll use different, most probably different parameters for the curve fit of the well impedance spectra. So this time I would be more inclined to use 1 Hz cut instead of 0. It all depends on the data. Let's go on like this. Once again, the design part of the operator is very similar. We see, first of all, we see the seismic spectrum in red. The green curve is the band-passed version of this black curve, and the blue curve, which is the operator, is the subtraction between the two. One noticeable difference is the operator in the time domain, for which you see that it is anti-symmetrical, and that is because we have applied a -90 degrees phase rotation to the seismic data. Okay. Once again, in terms of QC, we'll use the same tools. We'll extract 40 other traces using the same extraction settings, convolve the operator on the fly with the seismic traces, and see if we have a good reshaping of the seismic spectrum, of the colored inverted spectrum, I should say. The operator, once again, should be flat within the seismic bandwidth. It is not as flat as I would like it to be, so I would be willing to increase a bit the low cut frequency back to 16, maybe up to 18 Hz. It could be, like with on this data, that the QC operator is flat even further than the bandwidth limit. Here we have clearly a bandwidth limit at 65 Hz, and you can see that you see that the operator is flat, is well flat up to 90 Hz. But that since this will still be overfitting the data set, I'll reduce a bit the high cut value in order to avoid fitting too much noise. Even though since the amplitudes are decreasing with frequencies, it is far less a problem when running colored inversion than when running spectral blueing, because this part will have less amplitude than this part. So for colored inversion, the curve fit, the QC on the low frequency side is the most important. For spectral blueing, the QC on the high frequency side is the most important. And I'm almost done with this operation of creating the colored inversion operator. There's one more parameter I could adjust. If I think that the operator is too large in terms of time gate, so this operator has a size of about 200 milliseconds, it is possible to reduce its size by reducing the number of zero crossings, so by truncating the operator to a smaller extent. The truncations are only allowed at zero crossings. That's why the parameter you see is the number of zero crossings we do allow within the operator. So here, as a rule of thumb, any operator whose length is above 200 milliseconds is a bit large. And I am most often willing to keep the size below 200 milliseconds, like such or such setting. I'm going to save this colored inversion session, as I did before with spectral blueing. And I'm also saving the operator. So it's a colored inversion operator. Now that it is saved, once again, I can close this controlling window, and I'll come back to OpendTect, where the operator has been pre-filled here, and the only remaining steps I need to take is provide an attribute name. I'll press Add as New. That will give the attribute definition to the software, and I can compare the data, the inverted data, to my seismic volume. But since these are not the same quantities anymore, I will always want to use a different color bar. Just to keep in mind that one is representing impedance values, whereas the other one is representing seismic reflectivity values. This is my inverted section, my blued sections compared to the original seismic. Not very much comparable, the same quantities. So if I only look at this section, so you can see how one particular layer remains of about the same amplitude here. This layer is has very much the same thickness and about the same amplitude. Whereas if we look at the layer above, we can see that first of all it seems to dim towards this part, both in terms of thickness and amplitude. And if we look at the layer below, once again, its apparent thickness here is far different than the thickness over here or over here. So we can get very easily a new attribute cube, a new attribute volume, where we really have apparent thicknesses that are related to relative impedances. Now this is concluding my demo of both Seismic Spectral Blueing and Seismic Coloured Inversion workflows as they can be performed in OpendTect 4.0. And I'll now hand over the webinar to Adrian Benneton that will present us the upcoming developments for both spectral blueing and coloured inversion in the incoming release 4.2 of OpendTect.
Thank you, Arnaud. As Arnaud mentioned, my name is Adrian Benneton, and I'm the Managing Director of ArcCLS. ArcCLS is a software development company based in the UK, and we've been building OpendTect plugins for almost 10 years now, so we have a lot of experience with building plugins for OpendTect. Today I'm going to talk about an exciting new enhancement we've made to Seismic Spectral Blueing and Seismic Coloured Inversion. I will start my talk today, as Arnaud did, by opening up by using the Stratum 3 dataset, and we'll go into the attribute set window and select firstly spectral blueing. Again, I will set the input data, which is the original data set, which is the same as what Arnaud used, and as before we'll launch launch spectral bluing by clicking the Analyze and Create push button. Okay, this will pop up the usual set of charts that we have here on the left-hand side, but you'll notice that we have a new window called View Seismic. What I'm going to do, first of all, is to not go through the whole procedure of the steps that Arnaud did when he added the data, but I'm going to open a previously saved session. So I click the Open Session icon. That will bring up a list of previously saved sessions, and I will select this one at the bottom here. I will just don't save the previous session, and here we see a set of charts, and immediately we see in the View Seismic window the blued a blued line. Before I talk about that, let me just look at the charts here. We'll see that on the top left-hand corner is the original seismic data, a spectrum of 40 traces, and I've created a new chart immediately to the right of that, which I'm calling the blue seismic. Here I've loaded the alternative set of 40 traces, which we've applied the operator that we've generated through this process. Going back to the View Seismic, we'll see that we can see the blue section on top here, and if I toggle that off, we'll see the original blue, the original data underneath, and I can toggle that on and off, and we can see right away immediately the effect of bluing. Now, the importance of having this facility here is that we can do a lot of what-ifs. So if I was to open the design controls dialog, we can play around with some of these parameters and immediately see the effect on the blued seismic. So if I now change the smoothing operator length, you can see immediately that there is an effect. What I've done is I've reduced the amount of smoothing, and which is represented in the design operator chart down here as this red line, and if I go back up again, you can see there's more smoothing. I can go back and forth, and immediately you'll see the effect on the seismic, the View Seismic window of making that change. Now, all the other changes that we can make throughout the analysis, we can see immediately the effect that will have on the final data, which is obviously a powerful new facility. This allows you to do a lot more work at this stage, rather than having to save the operator, exit out of the bluing, and then applying the bluing in OpendTect. We can see it here and get it right before we actually finally exit from the program. There are a lot of other things that we can do. Is that we can change the color maps that we have here. So, for instance, I can go and select the bluing item, open up the edit palette dialog, and we can quite quickly change to a different color map. This is quite a neat, powerful facility. We can also add new sort of color points along this slider by just double clicking on it, and immediately a new point is added on the slider, and we can assign a color to that point. And here I've assigned a green color. We can do similar things anywhere along this slider rail and add a new slider and give it a color. So this is quite a powerful facility that we can have to build color maps that we can use at some later stage. we can also sort of turn on this to see the distribution of the data with this color map. In a similar way, we can get rid of any point by just double-clicking on it. And by doing this, we go back to the original color map. We can save these color maps. So if I switch to a new one, it will prompt me to save the edited color map that I had. I can't override the standard ones, but I can do a save as to a new color map. I'm not going to do that now. I'm just going to exit out. Okay. That really is a brief introduction to the new facility. What I'm going to do before I leave this now is to show you, I showed you bluing on top of the original. We can also add a new viewport by clicking Add Seismic. That name will change in the final release, and we can add a new viewport which will appear out to the right. At the moment it's empty, but I can go down to the new viewport and add a new, either the original or the blued volume. In this case I'll put the blued. The color map will need to be changed to the same as before, as the panel to the left. And what I'll do now is to toggle off the blued one on the left, so we see the original on the left with the blued on the right. Now they're not quite the same number of traces in this. One's going from 20 through to 100, and the other one's going from about just less than 20 up to 180. So they're not quite in sync with each other, and we can sort of zoom one separately from the other. But we can synchronize these two viewports by clicking on each on one of the viewports and then control clicking on the other viewport and then synchronizing, and something's not quite got wrong there. Let me see. Okay, unfortunately I toggled it off. So that is part of error, I believe. Okay, so we can also toggle on and off the crosshairs, and we can move this around. We see we got two crosshairs. I guess that's another teething problem with this beta release. I'm sure we'll get that fixed before we finally release the software. So let me just have the blued on the right and the original on the left, and we can now do various things, and they're both viewports are synchronized. Okay, I will now sort of exit out of this and quickly just show the same thing for colored inversion. Let me exit out, and I will select colored inversion. Same thing as before, select the original input seismic, and now select the analyze and create. And as before, I will open a saved session. And immediately we see the view seismic this time opened because I saved it that way with two viewports. They're not synchronized at the moment, but I can quickly select those and synchronize these viewports. So zooming and scrolling, and hopefully the crosshairs will work a bit better this time, and they do. Okay, well that's really all I have to say about this new facility. I think it's going to be a very powerful and very useful addition to this software. I will now exit out and hand back control to René. Rene, would you like to take control of the screen, please? Thank you.
Yes, actually, I'm passing the controls back over to Arnaud for a final conclusion.
Yes. I would conclude this presentation with the following. The simple theory between both spectral bluing and colored inversion makes these two workflows very robust. The solution is very often quite stable and doesn't vary much with changing parameters. They are both very fast to apply and can enable the interpreter to quickly generate new grids, new volumes, and 3D bodies that can be used for the interpretation. Both techniques can be done in a very early exploration stage, since they only require seismic data and most often very limited well data. The basic requirements are a few wells correctly tied to the seismic volume, so with a time depth curve, but no wavelet is required to be extracted for these two workflows. And they can, especially for seismic colored inversion, it can make use not only of acoustic impedance logs, but also any elastic impedance log for either little fluid analysis or for the inversion, the relative inversion of partial stacks. That would conclude our presentation. And if you have questions, Rene will unmute you, and please feel free to ask any questions.
Yes, please, you can ask your questions either by raising your hand and I'll unmute you, or you can type a question into the questions pane and I can read out your question anonymously. Please feel free to do either of those at this point if you have questions. Do we have any questions? Okay, here I actually just have one pop up. Let's see. I've had a few pop up. Okay, see the first question is, what is the minimum number of wells required for colored inversion? Would it be suggested to apply colored inversion in structurally complex regions, like different faulted blocks or different faulted blocks that vary in depths?
Well, there are multiple questions in here. First of all, both workflows are trace-by-trace processes. Therefore, if you have a steeply dipping block, it will not be very much an issue for either seismic spectral blueing or seismic colored inversion. Nevertheless, when it comes to the faults, if you have a fault throw of let's say 100 milliseconds or more, it could be problematic. That says that in general you should not apply spectral blueing, well, at least one single operator, if you have a time range varying over a second in general. So it has to be restricted towards your reservoir, and you have to extract the data relatively to your reservoir, but I don't think that fault throw are so much of an issue. And concerning the last question, the number of wells, very often you get a stable operator already with 3 to 5 wells. These are 3 to 5 is a very good starting point, but it's good enough to have an operator that is representative of your entire survey. If you have 10-20, you can always input 10-20 wells, but most often you will see very limited changes to your extracted mean impedance spectrum or mean well reflectivity spectrum. Does this answer question, Adrian? Yes.
Can I just add in on this one? With the new viewer, Seismic Viewer, you can see very easily the effect of adding more wells. And from my experience, that adding more well data has very minimal effect on the overall result. So certainly on this particular data set, obviously it will vary from different environments, and that will have an effect on how many wells you might want to use. But for this particular data set, we found that that with just one well you can get a pretty good result.
All right, well, thank you. And we have a reply from the asker who says, yes, thanks, that it did answer their question. The next question we have in line, I did pass along to you, Arnaud, so I'm not sure if you can see that, but I will read it aloud as well. It says, would spectral bluing be the best technique to use to enhance vertical resolution in areas of complex stratigraphic geology? For example, a section of overlapping cliniform features within a relatively thin gas sand, or are there other tools that can be used in OpendTect?
In order to increase the frequency spectrum, I would think, yeah, there are some frequency filtering tools in OpendTect, but there are mainly tools to apply a low-pass, band-pass, or high-pass filter. I think Seismic Spectral Blueing is from far the most relevant one because it will reshape the input spectrum, whatever it is, to your well data. It is the real only technique that remains calibrated to your well data, and therefore, yeah, I don't think any other more simple frequency filtering tool could give better results. And with respect to the structural complexity, that is not really something that reflects back into the frequency spectrum of your data. So whereas if you have everything that is flat and conformable, or something that is very structurally complex with cliniforms, most often it doesn't have a great effect on the spectrum. Hence, spectral bluing will work equally with both kinds of data sets.
Okay, we have a response saying, okay, great, thanks. So now the next question we have in the queue is asking when you should use the spectral bluing, when you should use the colored inversion, when each of them would work better, respectively.
Well, these two techniques have completely different goals. The one is made, if I go back at the beginning of the presentation, the one is made to get extra structural detail on the data, and also as pre-processing for relative impedance inversions, whereas the other one is much more targeted as interpreting the data with respect to lithologies and fluid content. So one works structurally, the other one is more with respect to reservoir properties and rock properties. If you are about to apply one, I would advise to apply the other one as well. But they really don't have the same goal. If one is applicable, it's very likely that the other one will be applicable too, and the opposite.
Anyway, thank you. I guess we have a lot of people who are wanting to be anonymous today. Nobody wants to ask the questions aloud, so we have another one to read off. This one is actually it's a short one. It's a true or false. It says, true or false, both methods apply a single filter to the subset of interest. And in parentheses, the filter is different for the two methods.
Yes, they both create one operator for every workflow. The operators are very different. especially because in spectral bluing we don't touch the phase of the data, whereas in colored inversion there is a phase rotation. But in general, for one application, you might want to apply to extract different operators in different parts of the survey. If you have two regions that are different geologically in your survey, you are always free to apply operators per area.
All right. Thank you. We have another question that is asking about the spectrum curves. It says, in the examples of the mean spectrum curves, the higher frequencies were cut on the blued curve. The high frequency noise was removed, but in this case, why was the resolution increased?
If we have removed, we tried to, yes, Adrian?
Sorry, did you want me to answer that question?
Yes.
The way that I view this is that because we're shaping the data to the reflectivity that we observe in the well, then we're somewhat depressing the low frequencies, which were previously obscuring some of the high frequencies. And that way we're able to see more high frequency data, which was on the original obscured by the low frequencies. So shaping it to the optimum shape of the reflectivity curve observed from the well data gives us more high frequency information, and thus makes it much more sharper. I hope that answers the question.
Let's see. Well, I don't see a reply on that yet, but I do have a question that is leaning more towards adding something as an OpendTect tool. And this is asking about the color table manipulation. That says the color table manipulation was nice. Can that be added as a general OpendTect tool? And we do have a response to that. If you'd like to go ahead and reply.
Yes. First of all, is it with respect to the color table manipulation from presented by Adrian? Because this will be part of both SCI and SSB plugins in the incoming 4.2 release. But since it is a separate, yes.
Can I just chip in on that? This is a separate facility that ArcSLS has put together with respect to colored inversion and spectral bluing. We prepared to discuss that with DGB as to making that facility generally available.
Okay, and the person who asked the previous question as well as this one, they both said that the answers were what they were looking for, so thank you very much for those. Okay. And we have a few more questions. So the next question is asking, what will you suggest? Which one is a preferable technique, spectral bluing or spectral whitening?
Well, definitely that's something I mentioned in my presentation. Spectral bluing should always be the preferred option because the Earth's reflectivity spectrum is not flat. So if you force your data to have a flat spectrum, you will simply not match your data, the true geology, I mean, behind. So seismic spectral bluing is definitely should be the real replacement of whitening. It's not a technique that is to be compared to spectral bluing. And if it is very well possible that from the data extracted in your wells, you see that the spectrum is rather flat. But well, in theory, it should always be slightly increasing in amplitudes with frequencies. You can find it rather flat over the seismic bandwidth, and in this case, applying spectral bluing will still be similar to applying spectral whitening. But the main problem with this is that most often this seismic well reflectivity spectrum is not flat and not even within the seismic bandwidth.
All right, great, thank you. And one more question. Are there any reliable techniques to convert relative acoustic impedance from colored inversion to absolute acoustic impedance?
Adrian, do you want to reply to this one?
Okay, we don't know of any technique currently. It's something that we've thought about looking into at some point, and we will certainly put that on our list of things to do if it's something that people really want to have.
Well, okay. The question asker just replied, thank you, so they're happy with that. Now, I think we have finally run out of questions. I had a lot of people asking questions this time, so that's great. If you would like to get in one last question before we end this webinar, then please hurry up and raise your hand or type in a question. Oh, yep, here we go. This question says, have you compared your results to other methods?
In the literature, there are some examples, not many, showing benchmarks between trace integration and seismic colored inversions, and most often it's very clear that colored inversion has a real edge on the other methods. And in general, you have a very good match between the time at which the techniques were employed and the quality. The more old methods have the least qualities, and since colored inversion is there is no new method, better method to apply relative inversion.
Can I just add in to that question? The colored inversion originally was supposed to be sort of an 80% solution. So basically, the idea is to try to develop an inversion technology that could be routinely done, and certainly colored inversion achieves that goal. It has since been observed that colored inversion is probably more like a 90% solution. Basically, you can use colored inversion 90% of the time, and you don't really have to go to the full-blown absolute inversion, and only really need to do that in rare cases. So colored inversion is a very powerful, simple, robust technique, and it's something that can be routinely done. I don't know if that answers the question.
All right, I'll wait for a reply to see if that does answer the question. Yes, it did. So if there are no other questions, I'll give it just a moment to see if anybody else types in one more. But if there are no other questions, then I would really like to thank our panelists and all of the people asking the questions. As I said before, this was a very active question session, so thank you for participating in this. This is for you, and if you just sit by and don't ask questions, it's not going to be as beneficial. So I'm very pleased with all of the questions. And I would just like to thank everybody for joining us today. And we will be holding our next webinar in December, on December 1st. And that topic, it's a nice treat for the end of the year. It will be covering pre-stack attributes, velocity gridding, and time depth conversions. So something to kick off the end of the year. So I do hope you join us on December 1st for that webinar. And for everybody here attending and participating as panelists and presenters, thank you very much, and thank you for joining us. See you next month.